Okay, good morning. So since this is the first time that we've had to do a remote or recorded class, I just want to make sure that you guys are clear on the expectations. So this is just like any other class. The main difference with the video is that I'm not going to actually pause and give you adequate time to solve practice problems because I know that you can just pause the video. Okay. So I will say pause here, work this practice problem, and then come back and check your answers. Okay. I will work through the problems though so that you can see kind of the process. Other than that, just recognize that you're responsible for the material just like if we were in class. Feel free to send questions. Like I'm happy to, answer emails during the day as you're working through it. That's just fine. And the other thing is that today will be the end of naming. So like I told you before, chapter 3 is kind of broken into two parts. Friday was like the introduction. Today is going to be naming compounds. And then Wednesday will be the calculations. So when you finish today's naming lesson, I would recommend that you go do the dynamic study module. That's the naming one. So remember, they're broken into two, and there's one about naming and one about calculations. They're both listed as due Sunday, but they're really, I should have just made the due date for the naming one earlier because it really can be done before Wednesday's class. So just the best idea is to give yourself that deadline and say, I'm going to do the naming one by Tuesday night, okay? Because there's really no reason to leave it. All right, so this one's just practice. So you can go ahead and pause here. This would be like a warm-up based on what we did last class. So, well, I guess, no, yeah, it is. Okay, so go ahead and pause here and then do these as a practice. I guess the only one that we haven't talked about, let me add this in, is that when we have the transition metals, so going back to our chart here, remember that all of these transition metals, at least the ones that aren't specifically circled here, these ones all have the potential for multiple charges to form. In addition to those, lead and, let's see, what's the other one that falls in that? I'm having a mind blank for a second. Lead and tin. Okay, so these two guys here, lead and tin, have the potential to form multiple charges as well, even though they're not a transition metal. So we very much separate these. So the ones that are highlighted in pink here are considered ones that will form multiple types of ions, meaning that they don't have a set charge. So you need to very clearly separate. We're going to talk about them as type 1 versus type 2 metals. So what I'm going to do here actually, just to emphasize this point, I probably have this later on in the slides, so it'll probably be repeated, but I just want to make it super clear, okay? So we're going to have type 1 metals, and these are the ones that have only one type of ion, one charge possible. And this is specifically the metals, because the non-metals, they always maintain their charge. They don't have any that change charge, okay? So I'm going to highlight the type 1s in yellow, okay? So it's these three transition metals plus the ones that we've already looked at. And then in pink, so I'll highlight that type 1. In pink is going to be the type 2, which has multiple charges possible. And this includes most of the transition metals as well as tin and lead. Okay? So you don't have to know what charges those type 2 ones can form. You just have to know that multiple charges are possible. You will always either be told the charge or you will be able to infer it from the chemical formula. That one's a little bit more complicated. We'll get to that in a little bit. But just recognize that we have these two different types of metals. Type 1, where there's only one charge possible, and type 2, where there's multiple charges possible. Okay? All right, so when we have compounds that are type 2 metals, they're going to list them either with the charge, so it might be written as vanadium 3+, or it might be written in words, vanadium, and then they'll put the charge as Roman numerals. Okay, so vanadium 3 implies vanadium 3+. Cobalt 3 implies cobalt 3+. Okay? Okay, so now you can go ahead and pause and do this as a warm-up. Okay, so remember with forming ionic compounds and determining the chemical formula, there's two basic steps. One, you need to write the symbol, determine the charge. So this would be based on the location on the periodic table, if it's a type 1 metal or a nonmetal. If it's a type 2 metal, then they're going to have to tell you the charge. And then you're going to have the formula to achieve a 0 charge. So this is like how many of each one do we need so that they balance out to have an overall charge of 0. So strontium, Sr, we'll go back up to strontium's here. So it's a 2+. Chlorine is a -1. Okay. Cesium is a 2+. It's right. Oh, sorry. It's a 1+. And sulfur is 2-. Aluminum is 3+. And oxygen's 2-. I'm not sure why I'm doing all of these, like doing the charges and the symbols first before I do the formulas, but it's fine. We'll go ahead and pause here and do the formulas. Okay, so for strontium, chlorine, strontium and chlorine, we're going to have 2 chlorines for every 1 strontium. So that's going to be SrCl2. And you can do that charge crossing thing if you want. So recognize that this is a 2 up here. That's what's going to cause it to be 2 chlorines. This is a 1 here implied. That's going to be 1 strontium. And that will always work as long as you reduce it down if possible. So like if it was a 4 and 2, you need to make sure to reduce that to 2 and 1. Okay, so when I talk about it, I'll say the charge crossing thing. That's what I'm talking about. All right, so on the next one, maybe we'll kind of emphasize that. So the 2 goes down here and the 1 goes here. So it's CS2S. Okay, again, you're just making sure it balances to 0. So 2 positives and 2 negative. Okay, so +2 and -2. That's how you get CS2. All right, aluminum and oxygen. This is where the charge crossing thing comes in real handy because, you know, having to figure out the least common multiple might get a little confusing when you've got these bigger values. So just take the 3 and put it down there. Take the 2 and put it down there. So your formula is Al2O3. And you can verify that if I have 2 aluminums that are 3+ and 3 oxygens that are 2-. This side adds up to +6, and this side adds up to -6. So overall, the charge would be 0. Okay, we said vanadium 3+ looks like this. Sulfur is S2-. So again, crossing charges, V2S3. And last, cobalt 3+ with bromine is a -1. So again, crossing the charges would be COBr3. Okay, so that is determining the chemical formula just based on the elements that are part of the compound. When we get to naming, which is what we're going to do now, naming the type 1s are really, really easy. The type 2s are fairly easy, just a little bit more complicated. Okay, so we're going to jump into that now. So I already talked about this. This is great. We already, I told you it would be somewhere a little bit more official looking, but we already talked about this at the beginning. Type 1s are going to only form one type of ion, and these are going to be the ones that are in that chart that we looked at. So where it labeled it, this one here. Okay, so those are the yellow, the yellow ones. And then type 2 are most of the transition metals and tin and lead. That's the ones in pink. Okay, and we're going to have two different ways of naming them. So let's start with type 1. It's very straightforward. You take the name of the metal, and then you take the name of the nonmetal, which is the anion, and you add "-ide", or you change it to "-ide". So calcium is just calcium, and fluorine becomes fluoride. That is literally all you have to do to name these type 1 compounds. So like if I scroll up to the ones we just did, this one here is strontium chloride, this is cesium sulfide, and this is aluminum oxide. Okay? I do not have to indicate how many of each thing there are because I'm going to be able to know that. Anyone who's studied chemistry is going to know that strontium is a 2+, chlorine is a -1, and therefore strontium chloride will always be SrCl2. When we get to covalent naming at the end, that's not the case. We can have carbon and oxygen forming CO. We can have carbon and oxygen forming CO2. Like, we can't predict how many of each element there's going to be. And that's why we're going to have to use prefixes when we do covalent compounds in order to indicate the number of each atom. Here, we don't have to do that. We can just say strontium chloride because strontium is always going to be +2, chlorine is always going to be -1, and so I know that strontium chloride is always going to have to be 1 strontium and 2 chlorines. Okay? Now, naming the type 2 are a little bit different because of that that ability for them to form multiple charges. Okay, so let's see. Yeah, I guess we'll go ahead and do this. The thing that's hardest about this is that you're going to have to be able to determine the charge based on the formula. Okay, so like if I was given, in fact, let's go up to our example up here. If I was given this vanadium 3 with sulfide, it would actually be really easy to name. I know the formula is V2S3, and the name would just be vanadium. I would say the charge in Roman numerals, 3, and then the same way that I changed the sulfur ending, I change it to "-ide", so sulfide, vanadium 3 sulfide. So that seems really easy, but they told us that vanadium was 3. What if we just had the formula? What if we had V2S3, and that's all that we were given, and we had to work backwards to figure out the charge? That's a little bit harder because we have to look at the formula and infer from the formula what the charge on vanadium was. Okay, so here's how we're going to do that. We're going to use the charge crossing thing in the reverse. Let me use a different color. So we're going to take the 2 and bring it up here and say, okay, sulfur. Was sulfur 2-? Yes, sulfur was 2-, so we know that that is correct because we know that that's what it was always going to be based on the periodic table. And then we're going to take the 3 and bring it up here and say, okay, vanadium was a 3+ ion, so I'm going to call this vanadium 3 sulfide. As another example, let's try another one, and then we'll work some in the practice and also look at the one they gave us in the chart. Let's pretend this was V2S4. 4. No, I don't want to do that. Let's just say V2S, okay? So let's say that this was the chemical formula. So I'm going to reverse the charges. I'm going to take the 2 and go back up here and say this is 2 minus. It's kind of like a little check that we do just to make sure that there wasn't something else going on. So we're like verifying that it matches what we would expect for the nonmetal. Then here we take this as an implied 1. We're going to take that back up here. So this compound would actually be vanadium 1 sulfide. Okay. Now, there's one more way that this works that gets really hard. So if you feel like you're going to get lost at this point, maybe come back to this and don't worry about it right this second. But I want to at least introduce the idea, but I don't want you to get hung up on it because it's the one thing that like will confuses people. So this part, little bit harder than type 1, but not impossible, okay? And pretty straightforward. This one, obviously, it's possible. It's just one step more confusing. So what if I had VS as my formula? And I need to figure out what the name is, so I need to figure out what the charge on the vanadium is. Well, when I try to do this reversing thing, what I find is that it's trying to tell me that this is a 1 and that sulfur is -1. And I know that that's not right. I know that it's a -2. So whatever charge I get for the vanadium, it must have been reduced from what the original charge was. And so I'm going to have to compensate for that. So it's almost easier to not do the charge crossing thing when you hit this point where they don't match. I can explain it to you if you want. Maybe later on I'll explain an example this way. But if you get to this point where the reversing the charges doesn't match up with what you know the nonmetal should be, then you probably want to approach it a little bit different. And I would like draw them out. So like write out 1 sulfur and know that that's a 2 minus because you can look it up on the table. And then write the 1 vanadium and ask yourself, what does the charge on that vanadium have to be if there's only 1 of them in order to balance it out to 0? And it must be a 2+, right? If there's 1 of each and we know that the sulfur is -2, then the vanadium has to be +2. So for this compound, this would be vanadium 2 sulfide. Okay. The other option is if you see this happening, you say, okay, whatever I get for this, I need to multiply it by the same thing that this was multiplied by. So like this one was multiplied by a 2. So if I cross this back and get a +1, I need to also multiply that by 2. I think that's probably a little bit unnecessarily confusing. So I would just do it this way and write them out. So let me give you one more example of that. I'll erase this one up here and do it up here. Okay, so one more example of this would be if I had, let's see, VS2. Okay, so if I gave you that formula and I said determine the name, you would start by taking this number here and bringing it up and seeing that it's a -1. Okay, you know that that does not match what you expected as a -2. So instead, let's write out each of these components of the compound and figure out what the charges must be to make it 0. So the sulfur, you know, and I wrote 2 of them because there are 2 of them, but I'm going to write them out like, two separate things so that you can see it a little bit clearer. So if this is my compound and I have sulfur with 2 minus and 2 minus, the question is, what does this have to be? Okay, that's got to be a +4 in order for them to all balance out. Okay, so this would be vanadium 4 sulfide. All right, so I promise that is the hardest that those get, is the ones where the charge doesn't match. And so you kind of know, all right, something happened here and it doesn't quite match up, so I'm going to do it slightly different to figure out what that charge was. You can also do it the way I said before, where you look at it and say, okay, this was times 2 what it, to get it to what it should be. So when I look at this one and I put the 2 up here, I'm going to say, nope, the real one has to be times 2 that as well. And that's how you would get to the 4. So you get to the same answer. It's just kind of 2 different approaches. Again, like I said, that is like the hardest of the type 2s. So if you want to come back and review this, you're definitely, would be helpful. But also, like, we can just do more practice problems and see it multiple times. That's what's going to make it really stick. Okay, so let's do that for the lead fluoride. Let's go ahead and do the charge reversing thing. So down here I have a 1. So this is -1. Remember, the positive always comes first and then the negative. So you know that, we're looking at the negative side when we look at the right side. Okay, and that's what fluorine is supposed to be. Fluorine is a -1. So this one worked out fine. So this 2 comes up here, and we say that it's lead 2 fluoride. So that was a good example, because it's like we did all the really hard discussion about the really hard ones, and now we're saying, listen, it's not always that hard. Sometimes it's just a matter of reversing the charges, figuring out what lead was, and then saying that in Roman numerals. Okay? All right. So at this point, I want you to pause the video, and you're going to indicate what type of compound this is. Is this type 1 or type 2? And then you're going to write down the name. All right. So the first one is type. We're looking at the metals when we determine the type. Don't forget. So all of these ones I've underlined, those are all main group elements, and they are not one of the 3 transition metals that has that single charge. So again, if you get confused at all, always go back to this to review that. The yellow ones are the ones that are type 1. They only have 1 possible charge. The purple, pink ones are type 2. They have multiple charges that you can't predict. Okay, so type 1, type 2. Which means when we do the name, this one's going to have a Roman numeral in both of these, because that's the difference with type 2, is that we have to indicate the charge in Roman numerals. For the type 1, it is like literally the easiest naming you could possibly do. You name the element, sodium. You name the nonmetal, oxygen, but you change the ending to "ide." So instead of oxygen, it becomes oxide. The next one, barium. Now, I might use examples in class or in the homework that aren't the ones you had to have memorized. If it's on the test, I will only use ones that you had to have memorized. The 1 through 36 plus silver, gold, and lead, or whatever it was. So this one becomes barium sulfide. Okay, let's do the last type 1, and then we'll go to the iron ones. So the last one, lithium. And then phosphorus becomes phosphide. All right, for type 2, we still go ahead and name the metal, and then we do the non-metal with the "-ide." So it follows a very similar method, but then you need to put something in the parentheses. You need to put that charge in the parentheses. Okay, so both of these are actually going to be iron, some charge, oxide. Okay, so we just need to figure out what the charge is. So let's start with the first one. Why did I make both of these difficult? Let's change this one. I'm going to say this is 2, Fe2O3. Okay, I don't want both of them to be complicated. So I am calling this a typo, and I'm saying that this compound should actually be Fe2O3. Okay? All right. So I take this number here, and I put it back up there, and I make sure that that matches with what I expect, and it does. Okay, so I'm good there. Then I look at this number here, and that's going to be my charge in the name. You can, rewrite it up here if you want, but it just is telling us it's already iron 3 oxide. So as long as the nonmetal charge matches what we expect it to be, then whatever number is down here, that's going to be the number in the Roman numerals, iron 3 oxide. All right, for the next one, we look at what's here and put it up there, and it's a -1. That's not what we expect it to be. So let's use my little method of writing out all of the components of the formula, FeO2, labeling the charges that we know they actually are. And you could do this for the other kind that are easier as well. You could do it for all of them. You could do it for barium. That would not be, you don't have to indicate charges there, so that wouldn't actually be useful at all. You don't need to know the charges. But you could have done that for this one over here. Okay, you could have said Fe, FeOOO, and then labeled the oxygens, 2-, and then had to figure out what these guys were to balance that out. It actually, if anything, is harder in that respect. But certainly when you get one where the charge doesn't match what you anticipate, then that's a good point to go ahead and write out each part of the formula. We'll put the charges on the ones you know, and then figure out what this has to be in order to balance it out. So there's 4- in the oxygens, so this has got to be a 4+. So iron 4 oxide. Okay. Next type. So, sorry, not to confuse things. There's one more type. So this instance, and it's really, you know what? I think I changed this last time, and I need to change it in my notes. I'm not going to call this type 3 because this could be type 1 or type 2, but we also are going to have something different in the anion. So remember, every ionic compound is made up of the cation, the positive side, and the anion. I want to see if I have a flow chart here. No, I don't have what I was looking for. I'll just have to make it up myself. That's fine. Okay, so you've got the cation and the anion, and with the, tell you what, I want a blank page so that this looks tidier. There we go. Okay, so for metals, you always have the cation and the anion. With the cation, you can have type 1 metals, or you can have type 2, and that's going to affect the naming, okay? With the one we're about to talk about, and this is why I'm going to not call it type 3, I'm just going to say that this is polyatomic ions. There are some times when the anion is just a regular nonmetal, but there are also a lot of times when the anion is what we call a polyatomic ion. Okay? So a nonmetal is like it's just oxygen or it's just fluorine or it's just, chloride or something. A polyatomic ion is when we have a group of elements that all form an ion together. So let's scroll up here to see some examples of those. We actually have a list here that's all of the ones that you're going to have to, I'm going to say, memorize. You're not actually memorizing them purely. You're making sure you know how to associate the name and the formula. So on the exam equation sheet, you'll be given a list of the polyatomic ions. You just won't be given their name along with them. So the hardest part about these is making sure you get all of the numbers right. Like this one's 2 and 3. You need to make sure the charges are right, -1 or -2 here. And those are going to be given to you. The thing that you have to have memorized is that you need to know what their names are so that you can go from the name to the formula. So like if I give you something with OH minus, you need to know that that's hydroxide. Or you need to know what the difference is between nitrate and nitrite. Okay? So when you're memorizing these names, there's a couple little hints. Some of them are obvious, like nitrogen. That one has ni at the beginning. So that's indicating that there's nitrogen. Lots of the endings for ones that have multiple compounds have endings of "ite" or "ate." Those are oxygen compounds, and they don't always indicate how many oxygens they are, but the 8 is always, and I'll write that up here, 8 is always the higher number of oxygens, and "ite" is lower number of oxygens. So for nitrate and nitrite, nitrate has 3 oxygens, nitrite has 2 oxygens. For chlorate and chlorite, chlorate has 3, chlorite has 2. And let's do one more example, sulfate and sulfite. Sulfate has 4, sulfite has 3. Okay. When we have other compounds where there's even more, like with this one here, we call the one that has 1 additional beyond the 8, we call that perchlorate. And then the one that's less, ClO, we call that hypochlorite. So it's like chlorite, but it's even further reduced in the number of oxygens. This is one where you want to put it in like a Quizlet, just to be familiar, because you're going to see pretty quickly, we'll name a compound and then you'll have to know what the formula is. So, maybe I say sodium phosphate. So you know that sodium is Na, and phosphate, you're going to have to know that that's PO4 3-. Okay? So you'll have the exam equation sheet to look at the list and like kind of rule out which one it is and verify the charges and everything. But you will have to, to know that phosphate is PO4 3-. Okay, so what's different about these? The main difference is that you just say the polyatomic ion name, you don't change the ending. So if we had NaNO3, well, let's do this example first. Oh, sorry, those are just examples of polyatomic ions, and maybe I need to be clear on that first. So what a polyatomic ion is when you have a compound that had covalent bonds. So NO3 looks like this, but it has gained an electron. So if we added up all the electrons of the nitrogen and oxygen and stuff, we would see that this one had 1 extra electron, and it got that electron from a metal that it was bonding with. So it actually has covalent bonds holding the nitrogen and oxygen together. But then when we pair it up with another ion like sodium, it's the positive and negative that are attracting that cause it to be a compound. So the formula of this one would be NaNO3, but the positive side is the sodium and the negative side is this whole thing, NO3. In fact, I would encourage you guys to write parentheses around the polyatomic ions because it just makes it a little bit easier to identify them and to remember that they are their own separate entity. Okay? All right, so that was the sodium nitrate, that first example here. When we name them, like if you were given the formula, it's really quite easy. You just say sodium for this guy, and then you identify NO3, and that's what you have to have memorized, that that's nitrate, not nitrite or something completely different. Okay. All right, for the next one, let's actually switch to this because this is a type 1. So if you notice sodium and magnesium, those are both type 1s. And so they're going to get named like we saw all the type 1s get named. It's just that the anion is a polyatomic ion. So magnesium, because it's a type 1, we don't have to say the charge. And then the name of the polyatomic ion, chlorate. For cobalt, which is type 2, we're going to have to say the charge. So it's cobalt, some charge, carbonate, because that's the name of CO3. So like, let's just go verify these on this chart here. Sometimes I write way too much stuff on here and have to erase it so we don't get confused. Okay, so the ones we just did were nitrate, NO3 minus. We did chlorate or chlorite? Chlorate, CO3 minus, and carbonate, CO3 2 minus. Okay? All right, so for the cobalt carbonate, this one, this is type 2, so we have to determine what the charge is. So when we look at the formula, COCO3, I want you to put parentheses around the polyatomic ion and then write the charge there so that you remember what it is. Okay? Then say, okay, if this was a 2 minus, because you don't get to determine these charges. They're determined, they're written down right here. So if the carbonate is 2 minus, what does the cobalt have to be? It has to be 2 plus so that they balance out. So you figure it out the same way. It's just that this one is listed in this chart and you're going to have these roughly memorized. I mean, you can always go verify it on the formula on your exam equation sheet, but like for carbonate, you need to know that it's CO3 2 minus, you know. But you can go verify that if you need to. So other than that, it works out the same way. It would just be like if I had cobalt and sulfur, right? I know sulfur is a 2 minus, so the cobalt would be a 2 plus. It's just that now the carbonate is substituting in for that sulfur. And that is what type 3 is ones that use polyatomic ion. But I don't like calling it type 3 because it's not different. You still have type 1 and type 2 metals. It's just another type of naming. And so I probably should get rid of that. Maybe your textbook uses that term. That's why I used it again. I'm not sure. Okay, so go ahead and pause at this point and work these practice ones where you're going to determine the name. And then we hopefully have some down here where you can determine the formula from the name. But we'll have lots of those back and forth. And I think I have even additional practice, like a PDF file. So if you do all of the homework and you still feel like you want more practice, you can message me and I can dig around in my files for that. Okay, name the following. So we're going to start with this first one here. K is potassium. It is a type 1 metal, so I don't have to put anything else. And then I'm going to put parentheses around this guy. And since you're not super familiar, you can go to the chart and figure out what the name of that one is. By the time the test comes, you'll know that that is nitrite. So the name is just potassium nitrite. Okay. The next one, type 1 again, so it's pretty easy. Calcium. This guy is called sulfate, so I'll just write calcium sulfate. Zinc. Don't forget zinc is actually a type 1. Even though it's a transition metal, it only has one possible charge, so we do not have to indicate a Roman numeral here. We just say zinc, and then we say the rest of the name, because we don't need a Roman numeral, even though it's a transition metal, because it's one of those few transition metals that is a type 1 that only forms one charge. It does not have multiple charges possible. Okay, and then this guy is nitrate. So zinc nitrate. We don't have to say how many there are of each because that is implied in the name, because we know that zinc is a 2+. So if we were going from name to formula, this is how we would do that. Zinc 2+, NO3 minus, and I would encourage you to always put parentheses around the polyatomic ions. And then we just do the charge crossing thing like we've done before, and it's Zn NO3 2. And now you kind of see the importance of the parentheses, because if I hadn't put those in there, it would look like 32. Like, I don't know what that means. So, like, you have to indicate that there's 2 nitrates. Because what this is telling you, this formula is Zn 2+, NO3 minus, NO3 minus. It's saying you have 2 of these little nitrate units. Okay, vanadium is a type 2. So I'm going to write vanadium. I'm going to put those because that's where my charge is going to go. And then I'm going to look up what this, or memorize what that polyatomic ion is, which is cyanide. And I'm going to need to determine the charge on the vanadium. So I'm going to reverse the numbers like we've done in the past. So this number, which is implied to be a 1, is going to go up here. And I'm going to double check that cyanide is a -1, which it is. If you go look it up on the table, it's Cn minus. So that checks out, which means that this 2 can go up here. And we can say that that's vanadium 2 cyanide. Okay, that is all of the ionic compounds. So if we let's skip over this molecular. Those are shockingly easy, so don't get freaked out by the fact that we still have more to do. So ionics are summarized here. You have the type 1 and the type 2. Type 1, type 2. Just recognize that sometimes the green part, the anion, might be a basic nonmetal that ends in "ide," or it might be a polyatomic ion. Whew, that was a lot of practice. Oh, it's the same page twice. I'm not sure what I did there. Okay, so let's talk about covalent compounds. That'll be our last thing. Hopefully I'm not running way too long. I have, sorry, that's one of the annoying things about when I record it, is that I'm always not perfect about the timing, so it might go a little long. Oh well, you didn't have to walk to class, right? It saved you a little time there. Okay, The biggest thing to remember is that molecular compounds, they mean covalent, are totally different than ionic because you can't predict the formula. As a reminder, I've said this like a few times, but like sodium chloride is always NaCl. It can never be Na2Cl or NaCl2. Like those cannot happen. But if I have two elements like nitrogen and oxygen is a great one because there's lots of nitrogen and oxygen compounds. Nitrogen and oxygen could be NO, it could be NO2, it could be N2O, it could be N2O4. It has like all sorts of combinations. So because of that, we have to indicate how many of each element we have. And the way that we do that is with these prefixes. So we're going to name how many there are of the first element with the prefix. And then we're going to name how many there are of the second element with a prefix. And the second element we're also going to change to "ide." That literally is the whole thing. So like, let's just do NO, this one here that I have circled, this one here. Nitrogen, okay, but there's two of them, so I need to say dinitrogen, and then oxygen, there's one of them, so I say mono, and then I change the ending to "ide." So dinitrogen monoxide. We don't say monoxide, we say monoxide, but whatever, you're not gonna mess that up because even if you said monoxide, I'm gonna know what you're talking about. And it's not like the spelling is gonna be wrong enough to be an issue. Okay. All right. The only one that's a little bit weird, the only rule here, and it doesn't look like I have this written down, so let me just write it down. Oh, it's right there. If the first element, let me erase some of these scribbles for you. If the first element only has one, we don't say mono. Don't use mono if it's the first element. So the perfect example of this is carbon monoxide. There's only one of each, but you know from experience, like in life, we say carbon monoxide. We don't say monocarbon monoxide. Okay, so that's a good reminder to you that we don't use mono on the first element if it's only one. That literally is everything about molecular compounds. That's why they're so much nicer to name, because you just use the prefixes and you change the ending to "ide." That's literally it. There's nothing more complicated. Okay, so go ahead and pause the video, practice naming those first three, and then practice determining the formula of the last three. Okay, so I'm going to go ahead and do this. Nitrogen. I'm not going to put the prefix because it's only one of them and it's the first element. So I'm just going to say nitrogen. And then fluorine will change to fluoride. And there's three of them. So mono, di, tri. Fluoride. I changed the ending to "ide." Okay. Sulfur. I'm not going to say mono because it's the first one. Di. Chlorine changes to chloride. Last one, 2 nitrogens. So I'm going to say di, nitrogen. 5 oxygens, which is pent or penta. Sometimes I've heard it done both ways with the oxygen. I'll show you what I mean in a second. So penta is the prefix for 5, and then oxygen changes to oxide. Sometimes we drop the A if the next one is a vowel. So you might see people say that this is pentoxide, not pentaoxide. I've seen it done both ways, so I don't know that there's one that's particularly right or wrong. Okay. Next one, if we're going from name to formula, hydrogen, it doesn't tell us how many. It must mean one because it's the first one. And then iodide is iodine, and there's only one of them, so mono, so it's just HI. Dinitrogen, so 2 nitrogens, trioxide, 3 oxygens. Hexaboron, hex is 6, so 6 borons. Mono is 1. Silicide is silicon with the ending changed to ide. So B6S. Okay, I'm going to consider that the end of today's class. I think what I'll do is think of this as a warm-up for next class. Although it is going to take a decent amount of time, I think I want to leave that as a warm-up. So I will give you the answers to this one when you come into class. If you want to do it now, like if you just want to kind of play around and do it now, you can just check your answers when you come in on Wednesday. Okay? All right. Try not to freak out too much. I know that was a lot of material. First of all, remember that the molecular compounds, the covalent, so easy. Okay? So keep that in mind that those are super easy. When you do ionics, follow this flow chart. Figure out, is it type 1 or type 2? And then either determine the charge if it's type 2 or just name it as is if it's type 1. So covalents are really easy. Type 1 ionics are really easy. The only ones that are a little bit difficult are the type 2. And then I would also say ones that involve polyatomic ions. So those are kind of like the 2 challenging things in today's stuff. So try not to be overwhelmed because there are some things that are very straightforward. It's just there's others that aren't quite as easy. Okay, so definitely try to do as much of the dynamic study module as you can, the one on naming. And if you're struggling with it, that's okay. We can do some more practice. But you do have all of the information at this point. And then I guess the other thing I would suggest is spend some time making a Quizlet, if there isn't one already, with the polyatomic ions. There probably is one on there, like in the public domain, that's, Dr. Christiansen's polyatomic ions or RMU polyatomic ions or something like that. Okay? All right. I will see you guys on Wednesday. Have a great rest of the day.